Let's investigate. All right, so the following objects do fall under the influence of gravity at a rate of g. G is roughly 10 meters per second squared. What's the actual number? Actual number, all right, the wiggle is going to be 10 meters per second squared. Actual number is 9.8 meters per second squared. So everything is going to fall at this rate. It's 9.8 meters per second squared. So the question is, why? All right, so we got the law of gravity. All right, so this is a statement of the law of gravity so far. All right, so the question is, objects falling at the same rate. Everything falls at this rate. So the question is why? Question mark. Newton came up with an interesting explanation for it. So that's what we're going to look at. All right, so here's the apple. And here's the earth right underneath. All right, guys, things are not drawn to scale. Okay. Apple is going to have weight. And the weight is caused by the force of gravity, Fg. All right, weight and the force of gravity, they are the same thing. So it's got weight, and the weight is going to be caused by the force of gravity. So capital G, the mass of the Earth. So the mass of the Earth, this big M, is the mass of the Earth, times the lowercase m, which is the apple, divided by the distance between them, squared. All right, so what do we know? Weight is the same as the force of gravity. So the gravitational force is the same as weight. So this term and this term, they're the same. They're equal to each other. So let's go. W is the same as Fg. W is mg. And Fg is the force of gravity. So it's going to be capital G, the mass of the Earth, the mass of the apple, divided by the square of the distance. Solve for G. Divide both sides by m. M. So cancel, 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 cancel. So the mass of the apple just dropped out of the equation. So here's the final formula. Question, what does R represent? R represents the distance between two masses, right? So what's the distance between the apple and the Earth, if that's the case? I'll give you 20 points for the best answer. So what's the distance between the apple and the Earth?
Is it the distance of their centers of masses?
Jack, give yourself 20 points. Beautiful. If you're not careful, I mean, if you guys are really good at selective listening, and most people are, if you're thinking the distance is 0, you missed the point. Distances are measured with respect to the centers of mass. Centers of mass to centers of mass. All right, distances are measured with respect to centers of mass. All right, so which means that you have to measure this distance with respect to the center of mass of the apple and the Earth. So this would be the distance, give and take. Guys, this would be the same as the radius of the Earth itself. So that distance is the same as the radius of the Earth itself, give and take. All right, so that's the distance between the radius of the Earth, R. All right, so what does that mean? If this formula is correct, it makes some interesting predictions. If it's correct, okay, we don't know if it's correct yet, but if it is, there are two predictions that it makes. It tells you how fast objects will fall, only depends on, it says how fast they will fall, depends on the mass of the planet or the star. Also, it says for how fast objects will fall, the rate at which they will fall depends on the size. So it depends on, inversely, it depends on the size, square of the size in this case. There are two predictions. The question is this formula correct? The answer to that question is depends. If you know the mass of the Earth and the size of the Earth, if you plug those numbers in, if this formula is correct, it should give you this answer. All right, so this one is an experimental number. So that little thing that you guys are looking at, that's an experimental number. This is an experimental number. All right, so it's observed number or the experimental number. All right, so let's say experimental. All right, so this is a measurement. It's experimental. And this is your theory. This is your prediction. All right, so this is your prediction. If the prediction is correct, it should give you the measure value. If the prediction is correct, it should give you the measure value. All right, so let's take a look. G, the strength of gravity. Here's the mass of the Earth. Here's the radius of the Earth. Here's what we're looking for. Here's the formula that Newton came up with. Plug the numbers in, you get 9.8. So what does it mean? Well, what that means is the predicted number and the experimental number, they match. That's it. This is called science, guys. Hence the reason why it's done mathematically. Prediction matches the observation. It's a numbers game. If the measured number and the predicted numbers are the same, then this theory is correct. That's it.
So is this how they're able to figure out the mass of planets just by the gravitational force? And
Give yourself 10 points. Absolutely, yes. That's how we know the planets, the masses of these planets. Absolutely. You're absolutely correct on that. That's one way of doing it, but this is definitely the correct way of doing it. All right, so it gets kind of stranger. This one is straightforward. Okay, so the more massive the planet is, the more you will weigh, right? The larger the gravitational pull becomes. So the faster you will accelerate, higher your acceleration is going to be. All right, imagine that there's a planet which is 5 times more massive than the Earth is. It's your 5G environment. Got it? All right, 5 times more massive is 5G. Okay, so that is kind of weird, and that kind of makes sense. But what's so weirder is this one, the second prediction. Now, the first prediction is more massive something is, more massive the star is, or a planet is, the larger the gravitational pull is. And vice versa, right? All right, so smaller the mass, smaller the gravitational acceleration. The weird thing is the second prediction. You got this inverse relationship. Okay, this is a mathematical prediction. You got this inverse relationship. Now, for a given mass, which means that your mass is the same, what would happen if you were to find a planet which has the same mass as the Earth does, except it's half the size? What do you expect? Okay, so inverse relationship means this, guys. If this goes down, this is going to go up. You find a planet which is half the size. All right, so you shrink the size, gravitational pull goes up. So how much does it go up? All right, so you find a planet half the size. How much does the gravitational pull go up? Okay, here's how you do it. You reduce the size by 2. What is 2 squared? It's going to be 4, right? So gravitational pull is going to go up by 4 times. So that's your 4G environment. So you find a planet which is 3 times smaller. If it's 3 times smaller, 3 squared is going to be 9. So the gravitational pull goes up by 9. 4 times smaller, it's going to go up by 16. 5 times smaller, it's going to go up by 25. It's a 25G environment. Now, just get this. This is kind of weird. I like the weirdness of it. Now, imagine that Earth, for whatever reason, it starts to shrink to 1/5 of its size. Something happens, nuclear war or something weird. All right, or the asteroid hits it, so the part of the Earth goes missing, big chunk. The next thing you know, what's left over is going to be 5 times small. Okay, that explanation didn't work. I just noticed that. I don't want to. Just imagine that the Earth just shrinks. Okay, now it works. Okay, I don't want to change the mass. I just want to shrink it. All right, so it's going to have the same mass. I'm just going to shrink it. If I shrink it to 1/5 its size, 5 times. All right, so what's going to happen? If you shrink it 1/5, 5 goes up, square that, so this is going to go up by 25. It's going to go up to 25 times the original value. So the gravitational force becomes 25 times larger. It's a 25G environment. Now, if you could survive in a 25G environment, if you could just survive that for 5 years or 3 years or a year, what would you look like? You would be shorter, and you would be also extremely muscular, right? You would probably look like Hulk. All right, so that's what, if you could just adapt to living in that environment, you would become extremely muscular. You would be extremely big. Your muscle density would go up, your bone density would go up. It would look really interesting in a weird sort of way. Anyway, it's 8:25. Take a short little break, okay, and then we'll take it from there. All right, so we know why the objects fall. They fall because of gravity. And we also have an expression. We also know why everything is falling at the same rate. Everything falls at the same rate because how fast the objects fall will depend on the mass of the planet. It's also going to depend on the size of the planet. So the next question is, does gravity extend all the way out to the moon? If so, where is the evidence? And so does gravity extend all the way out to the moon? Yeah, I'm hoping that this didn't get disconnected. Oh, cool. It's still connected. What do you know? All right, so here's the question. In theory, gravity does extend all the way up to the moon, guys, in theory. In theory. And in theory, because if it didn't, this would have gone in a straight line at a constant speed. And also the moon is accelerating. Okay, that's philosophy. All right, it's a self-consistent philosophy. Okay, where is the evidence that the gravity extends all the way out to the moon? So for us to be able to do that, we need to know exactly what this force is. And we need to be able to measure the effect of this force. All right, so how does that go? It goes like this. If Newton is correct, and if gravity extends all the way out to the moon, what should happen? What should happen is the moon should accelerate towards the Earth just like here. So you will get an acceleration, and this acceleration that you get will be the same as g, and we should be able to measure that g. All right, so we would know the distance to the moon. So this distance is going to be r that we got. This is the distance to the moon. And what I'm going to do is I'm going to place the moon right here. Moon is going to be located right here. So the moon would be accelerating towards the Earth here at a rate of which is g. And then we need to figure out what that g is and then measure it. All right, so that's what we need to do. What is this g from that distance? All right, so what is this value at this distance? And then once you got your theoretical prediction, just measure it. It's that simple. All right, so the thing that we need to do is just plug the numbers in. This is the distance to the moon from the center of mass of the Earth to the center of mass of the moon. The formula, plug the numbers in, and then we end up getting a very small number, which is 0.00273. 0.00273. Meters per second squared. All right, that's it. So this is the predicted value. This is our predicted value. All right, so this is our prediction. Okay, so the next step is somebody needs to literally measure this acceleration. If the measured acceleration matches the prediction, then gravity really extends all the way out to the moon. So, which means that the gravity that pulls the apple down is the same gravity that extends all the way out to the moon. Okay, now we got problems. The problem is this. This is a darn small number. It's very small. All right, so you got 0.00273. And then Newton wanted astronomers to measure this number 350 years ago. Did they even have the technology in order to measure something like that?